Hello everyone, welcome back. In this lecture, we shall see problem on heat transfer analysis in a pipe flow. We shall check the problem definition. This problem has been taken from Heat and Mass Transfer book, 2nd edition by Jonas Engel. Okay. Water is to be heated from 15 degrees Celsius to 65 degrees Celsius as it flows through a 3 cm internal diameter and 5 meter long tube. Okay, you can see the image here. The overall length is 5 meter and the internal diameter is 3 cm. Water enters at 15 degrees Celsius and leaves at 60 degrees Celsius, and constant heat flux is applied on the casing or on the walls of the tube. Okay, the tube is equipped with an electrical resistance heater that provides uniform heating throughout the surface of the tube. The outer surface of the heater is well insulated. All the heat generated in the heater is transferred to the water in the tube. If the system is to provide hot water at a flow rate of 10 liters per minute, determine the power rating of the resistance heater and the average heat transfer coefficient. Also find the wall temperature near the exit. Okay. Here they are supplying heat on the outer walls and they are asking to find the power rating required to increase the temperature from 15 degrees Celsius to 65 degrees Celsius for the volume flow rate of 10 liters per minute. Okay. First let us solve this problem through theoretical method and compare the results with simulation output. Let us start. We have to find out the properties of water at bulk mean temperature condition. Bulk mean temperature refers to the average temperature of this whole fluid domain. Here the bulk mean temperature Tb is equal to average of inlet and exit temperatures, which is equal to 15 plus 65 by 2, 40 degrees Celsius. Okay. So the properties of water at 40 degrees Celsius are given here. Thermal conductivity K, density ρ, specific heat capacity at constant pressure Cp, and dynamic viscosity mu. First, we have to find out the power rating Q. This is nothing but the net heat transfer rate supplied into the fluid. Okay. The net heat transfer rate Q is given by mCp delta T, where m is the mass flow rate, Cp is the specific heat at constant pressure, and delta T is given by Te minus Ta. That is nothing but the exit temperature minus inlet temperature. This is the amount of temperature rise for the fluid domain. We know that Cp or specific heat at constant pressure is defined as amount of heat required to increase the temperature of fluid or object by 1 Kelvin for unit mass, and the unit is given by joules per kg per Kelvin. When you multiply this with the delta T, then the unit will be multiplied by Kelvin, and when you are multiplying this with the mass flow rate, then it is kg per second. So cancelling kg and Kelvin, you will get joules per second, which is equal to watt. Therefore, the power rating has got the unit watt, or the net heat transfer rate has got the unit watts. To calculate the heat transfer rate, you need to find out the mass flow rate. They have given the volume flow rate. When you multiply this with density, we will get the mass flow rate. Therefore, mass flow rate is equal to density into volume flow rate. That is 992.1 into 0.01 meter cube by minute. We know that 1 liter is equal to 10 power minus 3 meter cube. When you multiply by 10, it will be 0.01. Okay. Therefore, mass flow rate is given by 0.1654 kg per second. Next, we shall substitute the values and find out the power rating. Q is equal to 0.1654 in the place of mass flow rate. Cp is equal to 4179 and delta T is 65 minus 15. Therefore, Q is equal to 34.56 kilowatt. So, this is the amount of heat required to increase the temperature of water passing through this tube at 10 liters per minute from 15 degrees Celsius to 65 degrees Celsius. Okay. Next, we have to find out the heat flux. Heat flux is nothing but the net heat transfer rate divided by the surface area, that is on the pipe outer surface area. So, outer surface area is given by pi d into L, pi into the diameter 3 cm into length 5 meter, which is equal to 0.471 meter square. Okay. Therefore, the heat flux is given by Q by As, which is equal to 34.56 divided by 0.471, which is equal to 73.46 kilowatt per meter square. Okay, we have calculated the net heat transfer rate and the heat flux. Next, we have to find out the convective heat transfer coefficient H and the exit surface temperature Ts. We know that the exit temperature is 60 degrees Celsius. This is the bulk mean temperature at the exit. For example, if you are assuming the temperature is constant throughout the exit phase, then it will be 60 degrees Celsius. If the temperature is 60 degrees Celsius at the end, and if it is uniform from the casing to inner region. But actually the temperature will be high at the walls and it will be low or minimum at the center region, because here heat is supplied from the walls to the inner fluid. Therefore, the profile will be somewhat like this. Here the maximum temperature will be present, that is Ts, and the minimum temperature will be present at the center, because here heat is supplied from the walls to the fluid, and the average temperature will be coming somewhat here. This will be around 60 degrees Celsius. So if you do CFD analysis and then plot, we will be able to get the average temperature as well as the temperature at wall as well as in the mid region. Okay, now they are asking to find the surface temperature Ts and also convective heat transfer coefficient H. Okay, we shall rewrite the properties. The properties are given here. Next, we have to find out the Nusselt number, for which you need to know Reynolds number and Prandtl number. First, we will calculate Reynolds number. We know that Reynolds number is given by rho v d by mu, for which we need to know the velocity and diameter. So diameter is given here. We have to find out the velocity. We know that the cross-section area AC is given by pi d square by 4, which is equal to 7.069 into 10 power minus 4 meter square. Next, we have to calculate the mean velocity. The mean velocity is given by volume flow rate divided by cross-section area. Volume flow rate is 10 liter per minute or 0.01 meter cube per minute. So dividing by the cross-section area, we get the mean velocity as 0.236 meter per second. Okay, now we have got the velocity. Next, we shall calculate Reynolds number. Okay, Reynolds number is given by rho v d by mu. So we can substitute the values of rho v, d and mu and find out Reynolds number. Here it is 10,760. So it means the flow is turbulent. So we have to use the Nusselt number formula for turbulent flow conditions. Okay. Next, we shall calculate the Prandtl number. That is mu Cp by K. We can substitute the values. Prandtl number is equal to 4.32. Since the flow is turbulent, we shall use the Nusselt number formula for turbulent flow, which is 0.0234 into Reynolds number power 0.8 and into Prandtl number power 0.4. Since the fluid is getting heated here, we are using 0.4 in the power of Prandtl number, else we will be using 0.3. Okay, we shall substitute Reynolds number and Prandtl number. Nusselt number is equal to 69.4. Next, based on the Nusselt number, we can find out the convective heat transfer coefficient H. Nusselt number is equal to H into d by K. Therefore, H is equal to K by d into Nusselt number. We can substitute the values. H will be equal to 1460 watt per meter square per degree Celsius. Okay. Next, we have to find out the surface temperature at the exit. We know that the heat flux Q is equal to H into Ts minus Tm. Ts is the surface temperature and Tm is the mean temperature or the bulk temperature. This is at the exit. Okay. We have already calculated Q, which is equal to 73.46 kilowatt per meter square. We know the mean temperature at the exit, which is 60 degrees Celsius. We shall substitute the values and find out the surface temperature Ts. Tm is 60 degrees Celsius. Substituting, we will get Ts is equal to 115 degrees Celsius. It means at the casing or near the walls, the temperature will be 115 degrees Celsius. 60 degrees Celsius is the average temperature at the exit. Actually, at the mid region, it will be still lower than 60 degrees Celsius. Okay. Now we have calculated convective heat transfer coefficient H and surface temperature 115 degrees Celsius. The net findings are tabulated here. Q, which is 34.56 kilowatt, H and Ts. All three are calculated. Okay. Next, we shall repeat the same problem in Ansys CFX and compare the results with theoretical calculation. I will see you in the next lecture. Thank you.